All right, we can get started. So hello, welcome to ESIC seminar series. This is John, the seminar coordinator, and together with me is Miss Kathy Medley. Kathy is our communication specialist, and Kathy and I will be today's moderator. We are so excited to have our speaker, Professor Noah Diffenbaugh, joining us from Stanford. Just so you know that the seminar is being recorded and it will later be published on our YouTube channel. Please be free to ask questions. You can do so by raise your virtual hand and we will unmute you. You can also send us text message. Let me give a brief introduction about our speaker. So Dr. Noah Diffenbaugh is a Carey Foundation professor and Kimmelman Family Senior Fellow at Stanford University. He studies the climate system, including the processes by which climate change could impact agriculture, water resources, and human health. Dr. Diffenbaugh has served the scholarly community in a number of roles, including as a current editor of the peer-reviewed journal Earth's Future and editor-in-chief of the peer-reviewed journal Geophysical Research Letters from 2014 to 2018. He has also served as a lead author for the IPCC and has provided testimony and scientific expertise to federal, state, and local officials. Dr. Diffenbaugh is an elected fellow of AGU and is a recipient of the James Houghton Award and William Collar Award from AGU. And he is a career award, he received a career award from the NSF. He has been recognized as a Copley Fellow by the U.S. National Academy of Science and as a Google Science Community Fellow. Let's welcome the speaker, and I will give the floor to Dr. Diffenbaugh. Dr. Diffenbaugh, please proceed.
Thanks so much, John. Generous introduction. So I'm excited to speak to you all today. Sorry that I can't do it in person, but thank you for joining online. And we have a lot of teaching and learning at home going on right now. So if the bandwidth gets rough, please just let me know. I apologize in advance. So I'm going to talk today about climate risk, and particularly extreme events and joint probability of extreme conditions. And I am going to warn you in advance, I'm not speaking about this because I have any solution or magical answer or even sophisticated technique. But the motivation rather is that not only is climate change occurring, but it is now very clear that it's occurring in a way that is causing not only greater frequency of extreme conditions, but also increased frequency of extreme conditions occurring simultaneously, both in individual locations and simultaneously across geographic regions. I will advance. So this, what I just been called compound extremes. And sometimes if it's not quite co-occurrence but rapid succession, sometimes will be called cascading extremes. And as I say, this is can be both jointly in space as well as across different regions simultaneously in rapid succession. And in many respects, we've been studying these compound extremes for decades, right? And many of the indicators that have been developed over the years, through which we now know that climate is changing in ways that impact people and ecosystems, are actually compound indicators, right? Such as drought indicators or wildfire weather indicators. But it's also clear that that the non-stationarity in the climate system is increasingly stressing natural and human systems. And in particular, we're seeing in recent years how the co-occurrence of conditions, either different ingredients coming together at the same time in a given location to create novel climate conditions, or as we saw acutely in California this past year with wildfires, as well as in recent years in California in the West, the multiple extremes happening within a region really stretch built around the baseline statistics. So the way that my research group thinks about these questions of climate risk management are really through the risk framing that tries to isolate the hazard from exposure and vulnerability. We're certainly not the only group that approaches it this way, but one of the advantages in answering these questions about the effect of non-stationarity on extreme events is that by isolating the hazard, it enables us both to frame scientifically tractable hypotheses, and the answers are also practically actionable, right? So society in general and decision makers in specific are working hard to try to better understand the role that climate change is playing in these rising risks, and is eager to take action, and by being disciplined in how we frame hypotheses and test hypotheses, there's potential to provide actionable information in addition to posing scientifically tractable hypotheses. So some of our work has been summarized and the large graphic here is from a recent primer, and the basic approach that we've laid out, is really kind of a four-step approach that can involve either just observations without any climate models, or also use climate models to generate hypotheses about the response of conditions to greenhouse forcing, and then we can use historical observations to test those hypotheses. And I'd like to start with kind of the beginning of where this research started, which is an older event, an older study, but really is an instructive point of departure for this question of co-occurring conditions in both in time in a given location and also across space, and really the ways in which non-stationarity in one aspect of the climate system can elevate the risk of extreme conditions. So California is now in drought again as we speak, and it was not so long ago that we experienced the most severe. So the California drought of 2012 to 2017, and this drought received a lot of attention in the scientific community, as well as was a major event that received sustained attention from both the state and federal government, as well as localities who were coping with it. And this is a graphic from the San Francisco Chronicle that took a graphic from our paper and made it much more accessible, visually accessible, with the one exception that they removed the vertical axes. But you get the point. Without the vertical axes from the graphic, right? California has been warming. There hasn't been any statistically significant change in the mean annual precipitation in California, and yet the frequency of severe droughts has been increasing. And if we look at those data in a scatter plot, what we see is that over the full historical record up to the point of the drought, when the paper was published, there was pretty even odds of low precipitation years coinciding with cool conditions. So these black numbers, if we look at the full historical record, low precipitation, right? The years that had low precipitation were about equally likely over the full record to either be warm or cool. And yet what the orange numbers show is that when low precipitation has co-occurred with high temperature in California's history, that combination is more than twice as likely to produce severe drought as when low precipitation co-occurs with cool conditions. And that result, which is a very simple result, just counting up the years, is frequently met with, well, of course, I've lived in California for 20 years, and all the it's always warm when it's dry. And that's true if you've lived in California for 20 years. Right? So California has warmed, as I showed you. And because California has warmed, low precipitation years are now much more likely to be dry. And that means that without any change in the long-term precipitation, the likelihood of severe drought has gone up. And in fact, at the time of this paper being published, it had doubled. So if we take out the most recent period, the probability that there is a drought is twice as high in the low precipitation years are also warm, is about twice as high. And the probability that low precipitation years produce severe drought is also elevated. So these again, this is very simple analysis, basically just counting the years. And what we find is that because of the role of temperature in moisture availability through evapotranspiration, through melting of snowpack, through evaporative demand in the atmosphere, that without any change in precipitation, the co-occurrence, right, the compound occurrence, right, you can use this compound extreme concept, the risk of drought has been elevated in California just by the warming. And that's the simple, very simple-minded detection. But what about attribution? So how do we test cause and effect? And this is will be familiar to this audience, right? So we use, in this case, the CMIP5 models for this particular analysis on the screen. And this is essentially, the experiment we'd like to run on the real world with and without human forcing, but using in fact, for the long-term mean annual precipitation, there's no, very little statistical difference with and without human forcing. In fact, there's a slight increase in the mean precipitation in the recent period in the simulations with anthropogenic forcing compared to the natural forcing. And the long-term warming is much more likely to occur with human forcing than without human forcing. So what is the effect on the combination of low precipitation and high temperature co-occurring? It's exactly what you would expect just from what I've already shown you. Again, it's very simple-minded probabilities, and we see that in the climate model simulation. So very high statistical confidence that the odds that low precipitation co-occurs with high temperature are higher in California in a world with human forcing than a world without human forcing. So that's, again, the very basic very basic sort of background on how we've approached just a simple-minded counting up of joint probabilities. There is, of course, a lot more nuance, a lot more complexity, especially when we try to understand more complex events, such as wildfire. So, as I'm sure you are aware from the national news, and perhaps even from the smoke that's made its way across the continent from the West Coast last summer, California and the West more broadly have been undergoing a series of extreme wildfire years. This is a picture from the August complex last summer, which became the largest fire in California's recorded history, more than 1 million acres burned. And the broader historical context is that the area burned in the West has been increasing for forested fires in forested areas. The area burned has increased approximately tenfold in the last 4 decades. And we know from work by John Amatzoglu and Park Williams, for example, as shown in the U.S. National Climate Assessment, that the aridification of landscape from the long-term warming is responsible for around half over the last 4 decades. So it's clear that climate change is making conditions in the West more conducive to wildfire. This is true in California as well. This is a figure from the Legislative Analysis Office from the state of California. So just the area burned going back into the mid-1980s, and you can see there's variability in area burned in California, but there is not only an increasing trend, but you can see that 2020 was just a phenomenal year, more than twice the previous maximum. And that August complex alone, as I said, burned more than 1 million acres. So that fire alone would have, been a large year historically. So in 2020, we had not only the largest fire, but also 5 of the 6 largest fires in California's history, and 6 of the top 20. And there were other fires that would have made the top 20 if not for the 6 that also occurred. So there were fires more than 100,000 acres that most people never heard of, such as the SQF complex, for example. This is the long-term context, and what happened in 2020. We had heat waves. We had very unusual lightning strike that happened in conjunction with this first heat wave in August that started so many of these lightning complexes. But then we had a second heat wave, the Labor Day heat wave, that also was associated with the Creek Fire, which is one of the largest fires in California history. And then we had this extreme smoke that blanketed much of the West Coast, on the order of 30 days. San Francisco had poor air quality for 30 straight days. And as I mentioned, the smoke made it across the country, particularly given that there were fires not only in California, Oregon, and Washington, but also, Colorado set multiple records during 2020 as well. And so again, we had conditions coming together in individual places. So for example, we had heat and lightning coming together in California, particularly in the Bay Area of California, following a very warm spring, and in many areas where these lightning complexes occur, it was at or near record low precipitation accumulation for the year when the heat wave happened and the lightning occurred. So compound coming together to create extreme conditions overall in individual places, but then also all of these fires happening simultaneously across the region. So again, both of those dimensions of compound co-occurrence. And it turned out that we actually had a paper on climate change and the likelihood of extreme autumn wildfire conditions come out right August 20th, literally within a week of these large complex fires starting by coincidence. And we were focused on the autumn conditions in particular because there are very strong winds that occur climatologically during the autumn in California. So there's an elevated risk from these offshore wind events, but historically, the wildfire resources have tended to kind of track the onset of the rainy season, and there has tended to be more of these fires in Southern California during the autumn, and wildfire resources have been released in Northern California. There's also the onset of the Southern Hemisphere fire season, and there's literally a limited number of aircraft that move. Fire suppression and response system has actually been built around the historical timing with this autumn relaxation. And what we've seen in recent years is these very large destructive autumn fires in California in 2018, in particular, overlapping in Northern and Southern California. In 2019, overlapping with the onset of the wildfires in Australia. And so it's really stressed both the national and the state, national, and international firefighting resources. So we were interested in understanding whether the probability of these extreme autumn fire conditions has been changing. And the boxes on these maps are the regions of the 2018 fires that happened in November and December of 2018. But the maps show the trends in these variables over the long term. You can see the warming of California during the autumn, and in fact, the August, September, and October show the steepest temperature trends statewide. So there's actually been amplified warming during this critical time of the year. We see long-term drying, which has less, in these analyses, much less statistically significant, although we now have work from colleagues showing that there has in fact been a delay in the onset of the start of the autumn rainy season in California. And then back to the concept of these compound conditions, the fire weather index, which integrates the temperature and precipitation. We can see that there's been a long-term trend towards increasing fire weather index during the autumn in the mean over most of California, and these are strongly significant. These trends are strongly significant for both temperature and for the fire weather index. So how might these trends come together to alter the probability of the kinds of extreme wildfire weather conditions that we've seen in recent years during the autumn in California? So here's a conceptual diagram from Daniel Swain earlier this year in GRL. And what you see is that even if the winds don't change, so this the dark line here, dark curve is the offshore wind pattern and the seasonality. And in this schematic, there's no difference between those lines on the top and the bottom. And what you see on the bottom, the long-term warming that we've seen documented in our work and other work, but including that amplified that we showed in the Gossadal paper, right? This extends the period of the year that has high temperature into the autumn. And then with the delay onset of the rainy season, you can see that both of these together extend the peak fire season, even without any change in the winds. And what we're seeing, this is schematically, but this is a hypothesis that's supported by those long-term trends that I just showed you, is that the preferential warming of the late summer and autumn is bringing hot conditions into co-occurrence with the peak offshore winds. And in fact, you may recall that it's, for example, in 2017, the World Series, which was Game 1 was played at Dodger Stadium, 103 degrees Fahrenheit, hottest first pitch for a World Series game in history, right? So 103 degrees Fahrenheit for the Fall Classic. So we're now seeing not only October but even November temperatures that are very summer-like. And even without changes in the winds, even without changes in precipitation, we're increasing the probability that there are record or near record fuel dryness when those offshore winds blow. In the Gossadal paper is that, in fact, the frequency of occurrence of days with extreme wildfire weather, those autumn seasons that have a high number of extreme wildfire weather days, those are associated with much larger area burned, right? So more than double the area burned in the years that have more than the median number of extreme wildfire weather days. And I should note that this is calculated throughout the calendar, right? So for the full calendar, 95th percentile threshold, the autumn seasons that have more than a handful of those days are associated with much larger area burned. And in fact, we find that the frequency of occurrence of those autumn seasons has been increasing steeply and has at least doubled in the past 4 decades. So this is the basis for our public statements that the frequency of extreme wildfire weather has increased during the autumn season in California. This is statewide, but as I've already indicated, the spatial co-occurrence matters substantially for the ability of the fire response system to effectively respond. And clear that the extension of the season, which they now consider there to be no off season, but in particular the extension of these extreme fire conditions into the autumn, has made it impossible for existing resources to respond sufficiently. We've seen that through 2018, for example, with the northern and southern California autumn fires burning simultaneously. We saw it many times this summer and fall in 2020, where there simply wasn't enough, wasn't the ability to contain the fires that were burning on the landscape in record or near record dry conditions. So we've tried to quantify changes in that for northern and southern California. And this is, again, the same research approach that you've now become familiar with for me, which is just counting, right? So we're just going through and counting up the number of years, in this case in the CMIP 5 ensemble, but just a fraction of ensemble years that have more than 5 autumn days that exceed the 95th percentile of the fire weather index. And you can see that increasing trend in the years that have these conditions both in northern and southern California simultaneously. And again, this is not a complex analysis, and it's not surprising given what we see in these historical with the mean warming and the mean increase in the fire weather index, that would push increase the frequency that both northern and southern California have extreme conditions simultaneously. And we see that higher, steeper increase in a higher emission scenario and a shallower flatter increase in a lower emission scenario. So we can look at the map view of that, and we can see that already, right, this current period that we're in now, this is the using the CMIP5 simulations, downscaled using John Abetsoglu's data. We can see, and John's co-author on this paper, we can see that we're in this period, we're already in a climate with elevated wildfire risk in terms of the days with the fire weather index exceeding the 95th percentile during the autumn season. We can expect that risk to increase substantially in a world of 3 to 5 degrees of global warming above the pre-industrial. And you can see that from in the far right map. We can also expect that level of intensification to be curbed at a lower level of global warming, right? So in a world, that is a Paris Agreement level of warming consistent with Paris Agreement goals and commitments, we find a substantial reduction in the intensification of extreme wildfire weather days during the autumn season in California, but notably still an intensification relative to the present. Right? So both of these are true. Both that unconstrained warming will lead to larger increases in these conditions, and even in a world in which the Paris goals are met, we can still expect further intensification relative to the present. So the question you're probably asking yourself at this point is there a more sophisticated way to approach this problem than simply counting up conditions at different grid points or over different regions? And this is a critical question, not just for the wildfire question, but also for a number of other climate-sensitive concerns, right? So we see this across not only the disaster preparedness and recovery, not just with wildfires, but with other types of disasters, but also in insurance and reinsurance, in supply chains in the globalized economy, agriculture and food security, and poverty more broadly. We're seeing where these co-occurring conditions are really stressing our preparation and response systems, and there's a lot of motivation for a more sophisticated approach than what I've shown you. There are a number of research groups who've been working on more sophisticated approaches, and certainly the copulas is one statistical approach that has been used for a number of years. So I'm going to close with a few results where we've attempted to try to answer this kind of question of co-occurring climate conditions, both in individual locations, multiple conditions coming together in individual locations, and also the co-occurrence of those multiple conditions in multiple regions simultaneously using this copula approach. So what we find at the global scale that just to expect, the probability of warm years has increased globally. The probability of dry years has not changed significantly at the global scale. But as the simple analysis of California already showed, using this more sophisticated copula approach, at the global scale, we find that the warming, just the warming alone, the increase in the probability of warm years, means that we're now in a climate where the probability of years that are both warm and dry has increased globally, and that increase does not occur in the CMIP5 simulations using only the natural forcing, and does occur in the CMIP5 simulations using both using those climate models. Right, this is the attribution, where we do find that increase in warm-dry probability is consistent with human forcing, not consistent with natural forcing. And that's the global scale. But the real question is are the odds of these multiple conditions occurring regionally, are they increasing for different regions simultaneously. So there's lots of different pairs of regions we could be interested in. I'm motivated for the wildfire. Actually, the U.S. and Australia are very key region pair for wildfire risk. We can, for food security, there are a number of region pairs that would be of interest, and I'll just call out one example here. If we look at China and India, which together, well over 2 billion people between those two. China and India have gone from a climate in which both of those regions simultaneously having a 2 standard deviation temperature anomaly and a dry year in the same year. Those two regions, both extremely warm and dry in the same year. The probability has gone from essentially negligible in the early 20th century to common, right? That both China and India have a 2 standard deviation temperature anomaly and a negative precipitation anomaly in the same year. This has a huge change in the hazard for a very large population that is a lot of exposure, that is very vulnerable to shocks to the food system, to the agricultural production, right? So you have high exposure, high vulnerability, and a very large change in the hazard that we're able to quantify using this copula approach. And again, coming back to this question of joint probability in space and time, and of both multiple climate conditions coming together simultaneously in a given region or location, as well as simultaneously in different regions. Right? This is an example of that, right? Like, so the risk for India, for example, of having 2 standard deviation extremely warm year coinciding with dry conditions, right? That is that's a compound risk for India as a region, and it's a compound risk for China as a region. And now we're able to quantify that spatial co-occurrence as well. As you might expect by now, this risk is likely to increase with further warming. And again, this is long-term warming, right? So even without changes in precipitation, even without changes in the probability of a dry year, and in some cases even with decreases in the probability of a dry year for some of these regions, we still see broad increases in the probability that region pairs that are critical for the global food system, increases in the probability that these region pairs experience these climate stresses simultaneously in the same year. On the left is that same 2 standard deviation temperature anomaly co-occurring with a negative precipitation anomaly. In the middle, we're seeing the change in probability of a 4 standard deviation temperature anomaly with a dry year, and on the right, 4 standard deviation temperature anomaly and a 1 standard deviation precipitation anomaly. So just the long-term warming is already leading us into a climate of unprecedented combinations of climate stresses occurring across multiple regions. And we also show in the paper that, as you would expect, that a lower level of warming will very likely reduce this intensification, as we saw with the wildfire conditions. We also see it with these region pair analyses. So again, as I've already mentioned, this question matters for a number of climate. And we can use this type of approach to quantify the joint probability of co-occurring extremes to a variety of different specific impact areas. So I've talked about extreme wildfire weather and basic conditions for agricultural stress, but of course we could imagine doing explicit calculations of agricultural yields or production shocks, and then a number of different kinds of extreme events with multiple climate variables. So my group has done a lot of work trying to analyze the different ingredients to specific extreme events, how water vapor and atmospheric circulation patterns, for example, come together to create individual extreme events. This kind of approach can help us to quantify using that ingredients kind of ingredients framework. We can imagine whether it's for quantifying the probability of the atmospheric conditions that created the Texas power grid failure, that severe cold. Are those the frequency of those conditions changing? Is that is it stationary or non-stationary with global warming for that extreme cold? For example, that's a question that has been asked recently. We could use this kind of approach, I think, in particular for the energy system and other. There are a lot of other examples where the baseline probabilities. So whether it's heat waves or other stresses, our energy system, right, is built around having a historical frequency of co-occurring extremes, and what this research is showing, and I think what these kinds of methods give us the potential for, is to more rigorously and reliably quantify how the changes in the conditions that matter for impacts, how they are changing, not just how they're likely to change in the long-term future, but how the global warming that's already happened has changed the risk. So with that, I will say thank you, and I'm happy to take questions if there are any.
Thanks, Professor. If anyone has any questions, they can either raise their hand or they can ask questions in the chat. I see two people are already asking questions in the Q&A, so I'll read one out loud. So this is from Mark Egan. He says, looking at the patterns of wildfire probability in California from climate models, it looks like probabilities increase within the same spatial pattern. Do you expect new areas in California that may suffer wildfires as climate change?
Yeah, so I think that refers perhaps partly to this map. And hello, Mark. Thank you for the question. The question of the changing risk and the vegetation, the different vegetation types and different ecosystems in which the risk is being elevated is a really critical question. And there certainly are a number of ecologists who are working on that question. And I think one of the real emergent features of the wildfires in recent years has been fires burning in most of the many of the ecosystems that had been perhaps most surprising for wildfires to be burning in. We've seen them in recent years. So tragically the Joshua Tree fires last year. We've seen a number of urban fires, with fires jumping ways. We're certainly seeing in chaparral ecosystems, grassland ecosystems, as well as forested ecosystems. We're seeing them in agricultural systems, the wine country fires year after year now. So, I am eager to hear from and potentially collaborate with ecologists that are trying to answer that question. This map in particular is of the fire weather index in vegetated areas. So there is a screening for land cover in the construction of these maps as we're plotting the fire weather index. So I think even even at the scale of these maps, which are very high resolution in terms of the climate information, there is still a lot of need for improved representation of the actual the ecosystem dimension. So I am sorry that I have not, if that is not a satisfying answer, but it is at least a long one.
Thank you. This next question is from Lauren Zamora. She says, great talk. Based on your work, do you have any idea of which countries would have the largest expected changes from their historical agriculture production based on changes to temperature and precipitation?
Yeah, so I have colleagues who have worked on that question in particular in terms of calculating the agricultural yields, for example. So David Lobel, who's in my department at Stanford, has been a leader in climate information and projecting crop yields. I think our in this study we did not go all the way to the finish line on that. So there's a couple of approaches one could take to take this analysis and repeat this analysis, but with more explicit representation of the impacts on the crops themselves. So one would be to run a crop model, suite of crop models, the AgMIP type. One could use the AgMIP data potentially, where those yield calculations have already been conducted using the CMIP climate models and a suite of agricultural models. And then the others use statistical approaches like David Lobel and others have developed to calculate using the climate model output to calculate production shocks essentially, and then repeat this analysis. So this is an inferential approach, just looking at the annual temperature and precipitation. But I think we're I won't go out too far out on a limb summarizing the agricultural impact literature, which is extensive. But I think that the main point is that we are seeing how, in the globalized food system, there are, very for how these production shocks affect, say, poverty vulnerability, for instance. And trade plays an important role. And trade policy and including real-time trade policy of how governments respond to these shocks play an important role in what the outcomes are for poverty vulnerability, for example. So another indirect but long question. Answer. Sorry.
Okay, this next question is from Mike Evans. He asks, Noah, have you ever compared the joint probabilities to what would be predicted from any available models that also simulate ecosystems and or wildfire? I'm not familiar enough with the literature or the field to know if they exist.
Mike, thank you for the question, and hello as well. Yeah, so there are, so we're taking a very agnostic approach here, and we're literally in it's basically, this index is basically built on antecedent temperature and precipitation, winds, and then some inference about the vegetation. To calculate a combination of fuel aridity and winds, both the speed and the humidity of the winds. So there's a compound metric itself, but there's nothing dynamic about the vegetation. So yeah, I guess I'd say similar to my answer to Mark. We haven't done it certainly. And I know there are ecologists that are working on that, both for implementation in fire risk models, but also in a key question right now for California is we've had so many really large fires in rapid succession in terms of, say, since 2017. Another key question now is the successional response, and we're seeing these fires in regions that have burned recently. So the Paradise region that was Northern California region I had the box around earlier, that region, saw, very, very rapid, large fire again in 2020, right? And so there's a lot of attempt to try to understand what areas are reburning, what areas are new fire, but in close proximity, and then what are the successional implications? And the Big Basin in the Santa Cruz area has received a lot of attention. And there's a lot of research monitor the succession, how much tree death there ultimately was in terms of the redwoods and how they respond. And then also, I know there's a lot of interest in the question of for these forests that have burned, whether the successional response is the same in the current climate. So there are some areas where I know ecologists are asking whether it's possible to get a forest in the current climate where a previous forest has burned. And I guess time will tell on that. But certainly with the hotter conditions, more arid conditions in some of these areas of California, that is a key research question.
Thank you. Yeah, and Mike did note that you kind of answered that question in your response to Mark Egan. He just wrote, just thinking it would be an interesting way to test validate those more complex models.
Yes, I definitely agree. And someone who developed those models would be in a great position to do that, Mike.
So this next question is from Dr. Zenking Lee. Dr. Lee asked, burning depends both on weather and fuel. As more fires burn out fuels that may have accumulated over a long time, it would reduce the chance of future burning. Is this factor considered in the prediction of future burning?
Yeah, so it's not considered updating of areas that are burned. I will say that I mean, this is literally taking the climate model output and calculating the index. So there's no dynamic interactions with vegetation at all. I will say that a large fraction of certainly there are forested areas that have burned, had stand clearing fires, and as I was mentioning a moment ago, right, how the successional response is an open question. There are also fires that are that have occurred in recent years in in shrubland, for instance, which with much more rapid regrowth, and actually a large fraction of if you look on the left, where we've quantified the area burned in these in the autumn years, actually for the autumn season, close to half of the area burned is actually non-forested areas for California. And so, certainly we got this very similar question from a reviewer as was just asked here, and there's some caveat in the paper in the discussion section about that. I think the sort of really extreme versions of the question are, if we take the area burned, say since 2017, right? You get, if you add up 27, a large, you get pretty much area of California, actually. And if you take, if you remove the agricultural land, urban areas, then there are back the envelope calculations that suggest that that all of the burnable area in California could burn within a decade if you had these rates of burning. And so that's kind of the extreme back of the envelope answer to the question is, well, if we continue at these rates, then it won't take long to have kind of burned through the standing vegetation. I am not an ecologist, but I don't think anyone is seriously considers that a serious possibility. I think the question is more, as we see these fires that are moving through the same subregion within a short number of years, I think we're still at the point of needing really careful analysis of what is new burning of vegetation that didn't burn before, and what is burning of regrowth. And I think that's an open question. But certainly, of course, there'll be some, for these, these maps are really future wildfire risk in terms of the maps, and obviously the vegetation response will be critical, and exposure and vulnerability will be critical. And I guess the last thing I'll say on this is just that, that all wildfires result from a confluence of conditions, and this is trying to measure the confluence of kind of climatic conditions that come together. But obviously, exposure and vulnerability are critical. There's never been a wildfire without ignition. The vast majority, more than 90% of ignitions in California are human caused, and there are a number of different causes of those human causes, right? So we've had a number from the electrical grid in recent years, which is the motivation for the public safety power shutdowns that PG&E has been doing in recent years. So now we're getting prophylactic blackouts in California when these kind of indicators are elevated in the short-term forecasts in order to avoid electrical grid fires or fires started by electrical grid. What was the largest wildfire in California's history prior to 2020 was started by a person hammering a stake in a field with a hammer and a stake, right? One person, one hammer, one's hammering a stake, human ignition, single spark from a single car, outdoor party with a pyrotechnic device being placed. All sources of have been sources of very large fires in California recently. So ignition is critical. And then obviously the state of the vegetation, the climatic conditions are not the only influence on the condition of the vegetation. Vegetation management, whether it's through controlled burn, through forestry practices, the vegetation management is critical. And of course, the exposure and vulnerability of structures, where we build, how we build, how we protect homes that are already built, those all influence the wildfire risk as well.
Thank you. So I have 3 more text questions in my queue, and I just want to remind the audience that if you wanted to ask a longer question or have a dialogue, you can also raise your hand, which you can, if you expand the participants panel, it's at the bottom, or you can just chat me, ask to be unmuted. So the first of the 3 questions I have is from Claudia to Baldy. Claudia says, thank you, Noah. I'm interested in your sense and experience about what counts when counting fails and copulus help, i.e. when we do not have enough model simulations to simply count robustly, or if it is more that copulus gives you a different answer than simple counts.
Thank you, Claudia, and hello. This is great. Hello, great to hear from so many awesome colleagues. Yeah, so I mean, I think in the we're being very conservative about what data we include in terms of data availability, obviously, as you can see from the maps. But we have a sentence in this paper that says, it doesn't quite say it this way, but basically, for the global scale, you get the same answer as if you just counted. Again, we don't phrase the sentence quite that way in the paper, but we do what you get for the observations here in panel F, is basically what you would get from just counting up the years that are warm and dry, and that's pretty. And that we actually had for the wildfire paper, the originally rejected version of this paper actually used the copula, the Sarhadi et al. Copula approach to do this analysis, and we get basically the same answer. The rejected figure basically looks like this figure. The numbers do at any rate. So I think really getting to the heart probably of your question, Claudia, gets back to where, sorry, I this is the worst, you may already know. click by click. Sorry for that. So really, where the motivation for this, this line of work on events really is the question Claudia's asking about, where where the conditions we're experiencing are out of sample. And I think that climate models, as we discuss in this paper, the climate models give us one big advantage, is that we can create many more versions of the historical climate than we're able to measure with the observations. And you can kind of see that, for example, in step 2 here. This is trends, but we also do it in step 3 with the probabilities. And so what we've tried to do is use the CMIP models to try to capture kind of structural uncertainty, and then use the NCAR large ensemble to try to capture the internal variability. So what I just said was a little bit tautological. I apologize. But I think the point here is that it gets very challenging when we're talking about these extreme events that we keep experiencing that are outside of our the envelope of the historical observations, right? So we have to make some, and probably Claudia should just be easier if Claudia just unmuted, because everything I'm saying Claudia knows more about than I do. But we have to make some assumptions about the functional form, where we have observations. We can try to use the climate models to create more histories of the climate system that then will help us not to have to make assumptions about what the functional form is out in the tail. But then we're stuck with these climate model biases that where the climate models don't really represent reality, particularly the more extreme the event is, then the less confidence we have in the physical processes that create those conditions. So I'd say we've my group's approach has been multi-pronged. One is to try to be really careful about how we're approaching the problem, and when I say that, I mean we're super conservative. Our approach is super conservative. We and that's sort of the starting position is it takes a lot to reject the null, and then to try to track all the uncertainty and the biases. And then the other is, you can see in this, right, this is the upper left here is geopotential height map, right? And so that the other thing we try to do is we try to focus on the physical processes, or just the aspects of the extremes where we have the most confidence in the climate models, because then we can use the climate models, as I was saying, to greater advantage for trying to understand the changes in probability. And then the last is to get back to the copula, where I think this is I showed this cartoon from the UC Irvine conference, and Agrichuk at Irvine, has been a real pioneer in using the copulas for these compound extremes, and indeed had papers on the California drought back in this era, right? And so I think where we've I think that the copula has gives us some ability to quantify the probability of the unprecedented conditions, where the unprecedented conditions are the co-occurrence of multiple different variables, but we still need assumptions about the functional form, and so it doesn't solve everything. All right, I'll stop.
Thank you. Yeah, and Claudia also says thank you. I asked her if she wanted to be unmuted, but we still have a few more questions, so she very graciously declined. So we have our next question is from Doug Morton. Doug says, NOAA, most of the increase in burned area in California and the western US is a result of larger fires, not more fires. Some of your metrics are agnostic to the duration of fire weather events. Have you looked at more time-resolved measures to examine this climate influence on fire size?
Yeah, so we've done a bit of that in generating what's on the left here. And yeah, so so I think that is an important point, and I think is actually gets to the heart of what I it's kind of the framing at the beginning of really my interest in this question. It really comes from the ways in which our response systems are being stressed, and the it's very hard to distinguish with area burned, right? It's this is very careful work by Park and John Park, and it's a really large fraction, right? Half of the area burned, but that's still only half, right? And I think one of the key questions, which gets to Doug's question, is the role of the decision making about responding to the fire in area burned. And the both the resources available for deployment, and then also where the literal decisions about like where the perimeters are set. And there's no question that in recent years the area burned has been influenced by the real-time decision making in responding to the fire. And what exactly that number is, how much of that, how much of the the cumulative area burned is from that, I don't know, and I don't know if it's possible to know, but it's one of the key influences on that gets to the heart of Doug's question about number of fires versus area burned, and there's no way to decouple both the resource availability and the decision making. And indeed, I will say that because of COVID, actually there was a lot of question about how to best respond in anticipation of the 2020 fire. And indeed, Senator Murkowski wrote a letter to the secretaries of Interior and Agriculture, essentially requesting modifications of the standard response approach due to the COVID risk, and asking for much greater mechanical suppression early on, et cetera. We had a citation for that letter. I can get you the link. I won't try to recapitulate it here, but the point is that I think even for 2020, the role that COVID played in the area burned, I think is an unknown, and is a key factor.
Okay, thank you. I have one last question from Xinjiang Liang. They say, hi NOAA, a great talk. For agricultural production, crop growth may depend a period of some length of poor consecutive weather conditions. How will you address such joint probability of compound extremes?
Yeah, so I think that's most like this fire weather index, which is calculated on using daily data, and so in this case we're calculating the FWI at the daily scale, and then analyzing the role. But someone could repeat this exactly using whatever metric is of most interest, and then one could use the simple counting, which is I've done a lot of and showed you a lot of, obviously. But one could also imagine, right? Because again, for these different whatever, I think the main approach is that whatever the metric that one prefers, then these kinds of statistical analyses can be used to quantify probabilities of different conditions. So I think in the case of the agricultural yields, right, again, one could run a model like DSAT that is mechanistic model that calculates the yields from the climate and other conditions. One could use this kinds of statistical analyses I mentioned earlier that Claudia has worked on with David Lobel, for example, or one could take more targeted climate variables than we have. Obviously, the annual, this is just for the annual temperature and precipitation, but one could, if one is confident in the climate metric that matters, if it's the heat accumulation during the grain filling season, using that metric, and the point here is really how do we calculate the extreme outcomes, particularly in a non-stationary climate where we know that the non-stationarity is affecting the probability of unprecedented conditions, but we are very challenged in calculating exactly how, and yet so many decisions are based either implicitly or explicitly on the calculation of the probability. And the default is when there's not an alternative, is to use the historical data with an assumption of stationarity. And we have a lot of decisions that are being made, both in the food system, in water management, in wildfire management, in infrastructure management, where the historical data with an assumption of stationarity is still being used because there aren't alternatives. And I'm not going to argue that this is a tractable alternative, but I think it does. I think all the questions that have come up really point to the need and the potential for improvement. And I think the one message from what we've experienced recently is that without that improvement, we're going to keep having really costly and disruptive.
Thank you. So that's actually all the questions that I have. So
okay.
Thanks so much for giving us this great talk and answering all of these questions. And thank you to everybody for attending and participating. So just join us next week as our seminar series continues. Have a great day, everybody.
Thanks, everyone. Really appreciate it.
Thank you, Professor. And we will send you the video recording once we got it. Thank you so much.
Sounds great, and I'm happy to send you the slides.
Cool. Thank you. Thank you. Have a great day, everybody.